Chapter 9, Spline. If we want to perform static error elastic analysis, including structure flexibility effect, we have to interpolate or spline the mode shape from the structure grid to the aerodynamic panels. And in order to activate the spline module, you have to specify solution 1 executive control command, and then you have to use assign FEM equals executive control command to import the structural finite element solutions. The spline method, we have a 5 spline method incorporated in the spline module. The first one is called infinite plate spline IPS. The car is called spline 1. The second one is called thin plate spline method, it's called TPS, and the car is called spline 3. And the third one is called beam spline, and the car is called spline 2. And then we have rigid body attachment method. The car name is called attach. And we also have a zero displacement method called spline 0. So the spline matrix transfer the displacement computed at structure G set to the aerodynamic K set by a spline matrix. So this is a G set mode shape, and then there's a K set mode at the ZONAIR panel model. Also, based on the principle of virtual work, one can prove that the transpose spline matrix can transfer the forces computed at the aerodynamic K set to the structure G set. So if you have a aerodynamic forces computed on the aerodynamic K set, use the transpose of the spline matrix, you can transfer the forces to the structure G set degrees of freedom. And then after you sum all the forces along X, along Y, along Z at the K set, then you will also sum all the forces along X, Y, Z at the G set. Those forces are guaranteed to be equal. So this is a conservation of forces based on the principle of virtual work. But this does not guarantee the conservation of moment. General guideline: all aerodynamic grids should be within the domain of the structural grid to avoid extrapolation. And so we have a spline 1, spline 2 for beam spline, spline 1 for the infinite plate spline, and spline 3 for the TPS 3D spline, attach rigid body attachment, and spline 0 with 0 displacement condition. And all the spline car refers to a set of ZONAIR panel IDs listed by the panelist 1, panelist 2, or panelist 3 card. And then spline 1, 2, 3 it also refer to a set 1 card. In the set 1 card, you list out the structural grid point and involved in the spline. So again, the spline is achieved by a component by component approach. We also have a plot mode card. So after spline, you can plot the interpolated mode shape on aerodynamic panel model. We have a card called spline M. You can save the spline matrix or retrieve the spline matrix. We have a card called spline F. You can generate a different spline matrix for force mapping. And we have a spline d.o.f. You can create or change the spline degrees of freedom of structure model. The IPS method is derived from an analytical solution of an infinite plate, and this infinite plate will first feed the deformation at a set of a structure grid point shown by the black circle, and it will project onto a plane, and then into a deformed infinite plane. So you will feed an infinite plane into the this deformed structure model, and because it is based on an analytical solution. Once we have this deformed plane, and we can, based on this analytical solution, to calculate the displacement at any point on the plane. Of course, we're going to plug in the aerodynamic grid point to calculate the displacement at aerodynamic grid. So in so doing, we can transfer the displacement from the structural grid points to the aerodynamic grid points. Okay, because the boundary condition of this infinite plane is at infinity, the deformation goes back to 0. So in general, the plane will gradually curve back to 0. This is the reason in all the spline method we want to avoid extrapolation. So all the aerodynamic grid point must be within the domain of the structure grid domain. And the IPS method requires at least 3 non-collinear structure grid to define a plane called the spline plane. And all aerodynamic grids should be within the domain of the structure grids to avoid extrapolation. The IPS method is the best spline method when splining between the plate-like structural component and the wing-like aerodynamic component, 0,7. If 2 structure grid points share the same location on the project spline plane, the spline matrix is singular. So the car for the IPS is called spline 1, and you give an ID, and this ID is used for error message output, and you give a CP because the IPS method needs a spline plane. So you define a contour car, and whose XY plane is the spline plane. Okay, so all the structure grid points listed by the set G will are projected on the spline plane for performing the infinite plane spline method. And set K, it refers to panelist 1, panelist 2, or panelist 3 card to list the aerodynamic panel ID. Okay, if those panels are on a 0,7 card, then you don't need to specify the contour card because the plane of the 0,7 can be the default spline plane. But if the aerodynamic model is modeled by sigma 4, sigma 3, then you have to define a spline plane using the contour card. And set G, you list out the structural grid point ID and to involve into the spline. And the DZ is a linear attachment flexibility. For the CP spline, we need to activate the least square method. So usually we need to define the DZ. But for the mode shape spline, usually you should put DZ equals 0. And EPS defines a small tolerance, and so the EPS times REFC. REFC is the reference core defined in LZ card, and if two or more structural grid point locations projected on the spline plane are nearly the same, in other words, within this small tolerance, and the spline matrix can be singular. So EPS is used to detect this condition. So you can use PLTMODE card to display the interpolated mode shapes on the aerodynamic model. Okay. And the thin plate spline generalizes the IPS method by incorporating some 3D XPath into the analytical solution of the IPS. The TPS method maps the deformation at a set of scattered structural grid point in a 3D domain to a set of aerodynamic grids. The TPS method is the best spline method when splining a set of a structural grid point located on the fuselage and the corresponding aerodynamic body component modeled by sequence 4 or sequence 3. So the TPS requires at least 4 non-coplanar structural grids, and so to define a 3D space. If all structural grid points are coplanar, the spline matrix will become singular. And similar to IPS, if two structural grids are very close and within a tolerance, the spline matrix can be singular. So the car is called spline 3. You give an ID. So because a 3D space does not need a spline plane, so we don't need this contour car, but it refers to a set K, and the set K refers to the panels 1, 2, 3 car to list out the aerodynamic panel ID, and set G you list out the structural grid involved in this 3D spline. And EPS, same as the IPS, it defines a small tolerance. So if two structural grids are located within this tolerance, it's a fatal error. Beam spline also you use an infinite long beam analytical solution to perform the beam spline. First, you have to define a spline axis. And the beam spline will project all the structural grid point onto this spline axis, because in the structure model, those grid points may not be along a same line. Okay, so you project onto this axis. Then for each aerodynamic grid, you will connect the grid to this beam by a rigid bar. So when this beam deform and twist, and this grid point will deform accordingly. In so doing, you can transfer the displacement and the rotation from the deform beam to the aerodynamic grid. Okay, so the spline axis is defined by the contour car, whose y-axis defines the spline axis. And again, if two structural grid points are too close, and it's a fatal error. So the car name is called spline 2, and unlike the spline 1 and 3, the beam spline requires both the translational degree of freedom and rotational degree of freedom for accurate displacement and slope spline at the aerodynamic panel. The spline 1 and spline 3 only needs the translational degree of freedom from the structure mode shape. Okay, again, set K refers to panels 1, 2, 3, and set G refers to a set 1 car to list out the structural grid point, and EPS is a small tolerance. The CID, it refers to a contour car, and whose y-axis defines the spline axis, the line of the beam. Okay, but this contour car must be located in the structure model coordinate. In other words, those contour car are those structure finite model before the ACSID and the flip entry of the LZ car are applied. Okay, and the curve is a curvature effect, and because the MSC notation does not include the curvature effect of the torsional stiffness of the beam, so by specifying curve equals 0, you can give a good you will become the spline 2 method of MSC notation. The next one is called attach, because if you have underwing store, those stores usually is very rigid. So the structural people sometimes they model the whole store by a long mass. Okay, they don't consider the stiffness; they only consider the mass. So you only have one grid point. Of course, in the aerodynamic model, you have to model the store. So the attach is that you will connect this point to every aerodynamic panels by a rigid bar. So when this point moves and rotates, the whole aerodynamic model move and rotates accordingly. So the car is called attach, and then you refer to appendix 1, 2, 3 car to list out the aerodynamic panel ID, and it refers to a structural grid point ID here. This is attached. The spline d.o.f, usually we use this for if you use the GVT measured mode to perform aeroelastic analysis. And then if you have a missile body, and then you use a accelerometer to measure the displacement along XYZ. But because it is a beam, so you have to use the beam spline. But the beam spline require not only the translational degrees of freedom, also the rotational degrees of freedom. So the spline d.o.f will create a rotational degree of freedom from the translational degrees of freedom. For example, in this case, DP-GRD is ID of the so-called dependent structural grid point, and also the displacement component of the structural grid, at which the modal displacement are related to that of other two independent degrees of freedom. So in this case, we want to create a rotational degrees of freedom about the y-axis. So the component degree of freedom is 5. Then the two independent grid point is 1 and 2. So 1 and 3. So we specify this grid point ID 1, this grid point ID 2, and we want to use the T3, which is component 3, and for at this grid, and also the T3 component at this grid. The distance between those grids is 10. So we use this equation to compute the slope. This slope will be the rotational degree of freedom at this grid point. So in so doing, we create a rotational degree of freedom for beam spline using the spline d.o.f class. And also sometimes when you do the generate a spline matrix for displacement spline and for the forces spline, the strategy to generate those spline matrices may be different. So you want to use this class SPLINEF to alter the structural grid involved in the spline, and to generate a force spline matrix. So you also can display the spline mode shape using the plot mode car, and then you give ID, and because the mode shape could be symmetric, anti-symmetric, or asymmetric. So you want to say, okay, what kind of boundary condition of the structural model is, and the mode you want to plot the spline mode. This is the mode index, and the maximum displacement is a fraction of the reference core defined by the IFC entry in the arrow Z car to define the maximum displacement of the deformed mode. This is because the structural mode is an eigenvector obtained by the structural analysis. The magnitude of the mode may not be of the same order as the size of the aerodynamic. model. So in order to control this maximum displacement, you want use this entry and times IFC. That will be the maximum displacement. And form depends on what kind of graphic software you have. Then you can choose that. Then you generate a file. Then you can plot the deform aerodynamic model for each mode. And the spline modeling guideline, most error in the error elastic analysis are attributable in the incorrect spline input. And so the spline is performed on a component by component basis. Selection of spline method depends on type of components in the ZONAIR model and the type of elements in the finite element model. So it's highly recommended that to select the structural grid point that are supported by a strong substructure, like underneath you have a spar, rib, and bulkhead for spline. Okay, so you never want to select a structural grid which underneath there's no substructure, because the boundary condition of infinite plane spline, and beam is the displacement equals 0 at infinity. Extrapolation can lead to a large error. Therefore, the aerodynamic boxes, the aerodynamic panel must be within the domain of the structural grid. Okay. So if the aerodynamic macro element is 0, 7, and the finite element model is a plane model, use spline 1. If it's a beam model, use spline 2. If it's a 3D structural grid, use spline 3. For single structural grid, use attach. And if you use the infinite plane spline method, and then this is the for example the CO7, and then the spline plane is the plane of the CO7. And for the structure model, you have a upper grid on upper surface and grid on the lower surface of the wing. If you include both upper surface and lower surface in the spline, for using the IPS method, IPS will project the upper grid and lower grid to the spline plane, and on the spline plane you may have two grid points that are at the same location. So this is fatal error. So to do this, you can either select the grid from the upper surface or from the lower surface, but not both. Then you may ask, the structural motion on the upper grid may go up, and at the lower grid may go down. So if I only select the upper surface, I cannot capture this mode. The answer is that the upper grid and lower grid are connected by either spar or rib. So to have this kind of mode shape is a very, very high order mode. So that usually have little impact on the aeroelastic solution. And also, if the structure is discontinuous, for example, structure you have a control surface, you have to spline the control surface and wing using two spline method cars. For example, you have a 10 structural grid on the wing, and then you have a grid 7 attached to the trailing edge flap, and grid 6 attached to the wing. And aerodynamically, you have a panel ID 9 and 12, which belong to this control surface. So when you do spline, you have to spline the wing, excluding the control surface. So in the side 1 car, you list out grid point 1, 2, 3, 4, 5, 6, and then 9, 8. Okay. And then the aerodynamic panel ID, you include 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Then you create 8 plate spline. Then second spline, you include structural grid point 5, 7, 9 and 10, and the aerodynamic panel you include 9 and 12 for different spline. So in general, all the aerodynamic panel must appear in the all the spline card once, but no more than once. But structurally, among different spline card, the structure grid point can appear twice, or more than twice. For example, in this case, the structure grid point 5 and 9 are involved in the wing spline, and 5 and 9 also involved in the control surface spline. Okay, so if the structure is discontinuous, you have to use more than one spline to account for the structure discontinuity. And another case is that if you have a continuous structure, and if you want to model the wing by 0.7, because each 0.7 only can model a trapezoidal-like shape, so in this case you have to use 2 CL7. And then if you want to do displacement spline, if you select all the panel on this C07, you select a structure grid from 1 to 9, and for this 07, you select grid point from 5 to 12, and if you do so, when you select grid point 1 to 8, and the infinite plane spline will define infinite plane, and for this spline you will create another plane which fits through from the grid 5 to 12, and those two infinite plane may not be the same plane. So in other words, you may create a discontinuity along here, discontinuity in slope. So for displacement spline, it is better when you spline this 0.7, you include the structure grid point ID from 1 to 12, and for this 0.7, you also use a grid point from 1 to 12. So those two splines, they share the same spline plane, so that will guarantee the continuous slope along the 207 for displacement spline. However, for force spline, you cannot do that, because if you want to transfer the forces generated by the aerodynamic model to the structure grid, if you include all the grid point 1 to 12 in the force spline, that means the aerodynamic forces created by this panel may have an influence on the forces at this grid. Okay, so for the force spline, you probably want to go back to, for this 0.7, you only refer to grid point, structure grid point from 1 to 8. This structure for this 0.7, you only refer to the structure grid point from 5 to 12. Okay. As I said, unlike the IPS and TPS method that only use the translational degrees of freedom, the beam spline requires both translational and rotational degrees of freedom. So often in the structure finite model, and the translational displacement are included in the A set and another set, and why the rotational degree freedom are not included in the A set. So exclusion of this rotational displacement for A set degree of freedom in the beam spline will lead to inaccurate spline result. And also in case of the GVT measure mode, that normally involves only the translational degree of freedom. So applying the beam spline method to the missile store body may lead to inaccurate spline result. So you have to use the spline d.o.f to create the rotational degree of freedom from the translational degree of freedom. Therefore, the beam spline can give you accurate spline result. Also, sometimes the structural people they model the wing. They only model the wing box because the wing box is a major load carry component, and they do not model the leading edge and trailing edge because they are not a major load carry component. They only include the mass effect of those leading edge and trailing edge region. So in this case, the structure model is smaller than the aerodynamic model, because aerodynamic model you have to model the whole wing. If you only include those structure grid in the spline and you are doing extrapolation, and that will lead to poor spline result. So to circumvent this problem, you have to go into the structural model. You create extra grid along the leading edge and the trailing edge. You connect this grid to the wing box using say RBE3 connection. And then you because you do not put the mass on those grids, so you do not change the natural frequencies of the structural model. But now, when you do spline, you can include those extra grid in the spline, so to avoid extrapolation. And the transposed spline matrix can transfer the forces at the aerodynamic grid points to the structure grid. And based on the principle of virtual work, the conservation of the total force is guaranteed, but it does not guarantee the conservation of moment. And so to ensure accurate force spline, it is recommended and the structural grid point select for the spline be coarser than the aerodynamic grid points. And so to give you one example, if this is the aerodynamic panel and you have two structure grids located in this on this panel, and because one panel can generate one aerodynamic force, we call FA. But when you transfer this force to the two structure grid point, you have a infinite amount of solution, and F1 and F2. When F1 plus F2 is guaranteed to be equal to FA. However, if you look at this force distribution, apparently is not correct. Okay, and so you wanna be you use a coarser structure grid than the aerodynamic point to avoid this kind of situation. And also selection of the structure grid at the structure hard point, meaning you have the grid point is supported by spar, rib, and bulkhead, is highly recommended. So the spline F car allows the selection of a structural grid point to be different between the force spline and the displacement spline. And this is one example. This is the aerodynamic model, and this is structural model. The structural model, the z-axis is along the left-hand side of the wing. The y is going up, and aerodynamic model, of course, the x is along the fuselage, z is going upward, y is along the right-hand side wing. So you have to transform the structural grid point into the aerodynamic model. So you want to use ACSID entry, which refers to in the LZ car, which refers to a contour car. You set up the contour car to transform the structural grid point into the aerodynamic coordinate. Then in the error car, you specify entry FEM grid equal to yes. Then you can display all the structural grid point on top of the aerodynamic panel model to verify this coordinate transformation. And this generic transport aircraft, because the wing is constructed by a wing box model that has grid point on the upper and lower wing skin, and so the TPS is ideal spline method for the wing. and TPS does not require a spline plane. But know that because they only model the wing box, so you have to put an extra grid point along the leading edge and trailing edge of the wing, and connect this grid point to the wing box by RBE3 to avoid extrapolation. And the fuselage of the structure model is constructed by a beam, and the beam spline spline 3 is used for the fuselage. All C-4 and C-3 elements of the fuselage aerodynamic model are included in the panelist 2 car. And the horizontal tail structure model are modeled by 2 beams. Okay, one beam here, one beam there, and similar to wing, extra grid point along the leading edge and the trailing edge are connected to the beam model using the R-bar element. So you can and then you can use IPS for spline, for splining the horizontal tail and the vertical tail. And the spline plane of the IPS must be in the structural coordinate. So it's also this contour count is defined in the structural coordinate, not in the aerodynamic coordinate. And elevator and rudder create discontinuity in slope of the structural model. They must be splined separately from the horizontal tail and vertical tail. The IPS also are used for the elevator and rudder spline. The engine nacelle and pylon in the structural model is modeled by a single point with a long mass. So this is ideal case to use attached. May create a discontinuity in the spline model between the pylon and the wing lower surface. But this is fine because we use the transversing boundary condition. So even you have a discontinuity in the spline, but when we use the transversing boundary condition, that will not introduce any problem. So finally, you use a PLTMODE card to look at the spline mode, and this is the end of the spline module.